Hi everyone! Today I'm going to walk you through the notes, Other Roots Day 2. The first part we're going to talk about rationalizing the denominator. What that means is that we want to make sure that when we simplify completely, we have a rational number in the denominator, not an irrational number. So remember that when we simplify, when we had the square root in the denominator, it was simple. We just multiplied the numerator and the denominator by that radical, because the square root of 3 times the square root of 3 is the same as the square root of 3 squared. And we have 2 radical 3 in the numerator. And the square root of 3 squared is just 3 because square and square root cancel each other. So we end up with 3. And we have 2 radical 3. So what's great is now we've just rationalized the denominator. We now have a rational number 3 in the denominator, whereas we started out with radical 3, which is an irrational number. Now, let's say we had the cube root of a number. Would that same technique work? Well, let's see. If we had the cube root of 4, let's say, and if I wanted to multiply that by the cube root of 4, that would be the same as the cube root of 4 squared. However, the cube root and something squared are not inverses of each other, so they don't cancel out. So, what are we going to do? So our goal today is going to be to rationalize the denominator, and what we're going to try to do is we're going to find a way to multiply the numerator and denominator by a number that will make it a perfect root. So we're going to start with cube roots today. So we're going to make a list of the perfect cubes. So let's write that over here. We have the perfect cubes. So we know that 1 times 1 times 1 is 1, 2 times 2 times 2 is 8, 3 times 3 times 3 is 27, etc. We're going to generate a list here. Okay. So in the denominator we have the cube root of 3. 3 is not a perfect cube. So we need to think of a number that is a perfect cube that's divisible by 3. So if we look at our list here, 27 is a perfect cube and it's divisible by 3. So we want to think to ourselves, 3 times what is going to give us 27? So 3 times 9 is 27. So we're going to multiply the numerator and the denominator by the cube root of 9. When we do that, remember that we multiply, so 2 times the cube root of 9 is 2 times the cube root of 9. And make sure that when you have your index of 3, it's with the radical and not with the 2, so it doesn't look like 2 cubed. And then when the indexes are the same, so we have the cube root and the cube root, we can multiply them. The values underneath the radical, the radicand, and we have the cube root of 27. Now that's really helpful because the cube root of 27 we know is just 3. So this completely simplified is 2 times the cube root of 9 over 3. We just rationalized the denominator because we started out with the cube root of 3, which is irrational, and we ended up with 3, which is a rational number. So this is our simplified answer. Let's look at example 2. So we have the cube root of 1/2. So if we remember, we can take anything that's underneath a radical as a fraction and split it up into the numerator and the denominator separately underneath the radical. So we have the cube root of 1 over the cube root of 2. Now, the cube root of 2 is an irrational number. It's not a perfect cube. So if we were to try to figure out what it is, it would be a decimal. It's irrational. So we're going to think of a number that is a perfect cube that 2 goes into evenly. So let's look at this list. So 2 goes into not 1, but 8. So 2 times what is 8? So we're going to multiply both the numerator and the denominator by the cube root of 4, because 4 times 2 is 8, which is a perfect cube. So in the numerator we have the cube root of 1 times 4, which is 4, and cube root of 2 times 4, which is 8. And this simplifies to the cube root of 4 in the numerator over the cube root of 8, which is 2. Now let's look at example 3. The difference here is instead of the cube root, we have the 4th root. So we're going to make a list of our perfect 4th powers here. So our perfect 4th powers. So here we're thinking of a number times itself 4 times. So 1 times 1 times 1 times 1 is 1. 2 times 2 times 2 times 2 is 16. 3 times 3 times 3 times 3 is 81. You get the idea. I'm just going to list a few of them. Okay, so we have the 4th root of 5. 5 is not a perfect fourth root. Any number times itself 4 times is not going to give us 5. So our goal right now is going to be to try to rationalize the denominator. So we need to think about that list. What number here does 5 go into evenly? So 5 goes into 625 evenly. 5 times 125 will give us that 625. So we're going to multiply the numerator and the denominator by the fourth root of 125. Fourth root of 125. So in the numerator, I have the fourth root of 250 over the fourth root of 125 times 5 is 625. And the fourth root of 625 is 5. So our final answer is the fourth root of 250 divided by 5. So we took our original value here in the numerator, which was irrational, and we've rationalized it because we ended up with a rational number in the denominator. Let's take a look at example 4. It's a little bit different because we're dealing with variables. The first few examples dealt with just numbers. So if we take a look at example 4, we have the cube root of 2x squared. So we know that 2 is not a perfect cube. And we know that x squared is not a perfect cube because the exponent needs to be a multiple of 3. So if we had to the third power, to the sixth power, to the ninth power, etc. So we want to think of the number first. So 2 times something is going to give me a perfect cube. So if we look at our perfect cube list, 8 is going to be a nice number for us to work with. So we know we're going to multiply the numerator and the denominator by the cube root of 4. That's going to be part of it because the cube root of 4 times 2 is going to give us that 8. Now we have x squared. We need an additional x to make that an x cubed. So I'm going to multiply it by the cube root of 4x and the cube root of 4x. Remember, with your properties of exponents, that x squared times x, when we multiply with the same base, we add the exponent, so this would give us our x cubed. So what we would have here is we would have 4x multiplied by the cube root of 4x over the cube root of 8x cubed. So if we simplify, we get 4x and then the cube root of 4x underneath the radical. The cube root of 8 we know is 2, and the cube root of x cubed, so when you think about it, what number times itself 3 times, or what value times itself 3 times is x cubed, is just x. But we're not quite done here because we can simplify. We can simplify what's in front of our radical with our denominator. So we have 4x divided by 2x here, and we can simplify that to become 2 times the cube root of 4x. So we're going to be looking at some examples today with numbers and variables as well. So let's take a look at example 5. So in example 5, we have the cube root of 5 divided by 3x. So again, remember you can split this up, so it's the cube root of 5 over the cube root of 3x. So we need to think of, first of all, a number and a variable for this problem because we have an irrational number in the denominator. So 3 times something, 3 times a number, has to give us a perfect cube. So if you look at your list of your perfect cubes up here, 3 goes into 27 evenly, so that's going to be really helpful. So if we multiply the numerator and the denominator by the cube root of 9, just thinking about the numbers for a second, that's going to give us 27. But we have a single x. We need to get it to be a perfect cube. So I want to multiply it by x squared as well. Because if I multiply by x squared times x will give me my x cubed. So if I continue simplifying, I have the cube root of 9 times 5, which is 45x squared, over the cube root of 27x cubed. And if I simplify here, I have the cube root of 45x squared over the cube root of 27 is 3, and the cube root of x cubed, so cube root and cube cancel, we end up just with x. And that would be our final answer for example 5. Let's take a look at example number 6. Okay, we see that we have this 4x in front. It's just 4x times that value. So what we can do, remember, is we can split the fraction so the cube root will go over what's in the numerator and the denominator. So we have 4x times the cube root of 3 over the cube root of 32x squared. Okay, so we need to think of a number that 32 goes into evenly that is a perfect cube. So if you take a look at the list above, we see that 32 goes into 64 evenly, and 64 is a perfect cube. Now 32 times 2 is going to give me 64. Now I have x squared and I need it to be a perfect cube, so I'm going to multiply it by x. So what I have here, I'm going to multiply the top by the cube root of 2x and the denominator by the cube root of 2x. So I end up with 4x times the cube root of 6x over the cube root of 64x cubed. So now when I simplify, I have 4x and the cube root of 6x over 64. The cube root of 64 is 4. So in the denominator we have 4, and the cube root of x cubed is just x. But we can simplify because we have here in the numerator and the denominator 4x divided by 4x just reduces to 1. So our final answer for this problem is the cube root of 6x. Okay. So that's how we rationalize the denominator when we don't just have a square root when we're dealing with other roots. Okay, if we move on to the next page, I'm going to start some of the practice you do. This is mixed practice from a few lessons the day before and also radical equations. So we're going to work through the first 5 examples together, and then you're going to practice for homework number 6 through 15. So let's take a look at number 1 on the next page. So what we're doing here is we are making sure to simplify completely, and we're going to leave our answers in simplified radical form. So 3 to the 1/4 power times 27 to the 1/4 power. So remember that when something is raised to the power of 1/4, that's the same as taking the 4th root. So we have the 4th root of 3 times the 4th root of 27. So remember, when the indexes are the same, we can multiply. So we have the 4th root of 81. 81 is a perfect root of 4, because when you multiply 3 by itself 4 times, 3 times 3 times 3 times 3, you get 81. So the 4th root of 81 is 3. For number 2, we have the 6th root of 36. There's no number when you multiply it by itself 6 times will you get 36. But remember that 36 is the same as 6 squared. So we can rewrite this as 6 squared, and then we have the 6th root of that. And remember that when you have the 6th root of something, it's the same as raising it to a power of 1/6. So we have 6 squared to the power of 1/6. Now remember, when you have a power raised to a power, you multiply the powers. So we have 6 to the 2/6, or 2/6, which is the same as 1/3, which is the same as the cube root of 6. And we can't simplify that further. That would be our final answer. Okay, let's look at example 3. Here we have the cube root of -56, x to the 6th, y to the 7th. So we're going to be working with variables, but it's going to be a little bit more complicated because the powers are larger. So the first thing you want to do is you want to separate this expression underneath the radical into 2 separate radicals, one with the perfect cubes and on the other side the non-perfect cubes. So if you take a look, we're going to kind of split this into 2. So we have the cube root. So if you think about 56, is there a number that 56 is divisible by that is a perfect cube? Well, 8. 8 is a perfect cube, and 8 goes into 56 evenly, so we have -8, okay? But on the other side here, -8 times what is 56 is 7. So over here, I'm going to write that on this side I have my perfect cubes, and on this side I have my non-perfect cubes, just so you can see what we're doing. Okay, now let's look at the variables. So we have x to the 6. So we want to think in terms of 3s. So we're dealing with the cube root. X to the 6 is the same as x cubed times x cubed, because when you have the same base, you add the exponents. So what I'm going to write here is x cubed and x cubed. So there's no other x's left, so we don't need to put anything in the non-perfect cube side. Y to the 7th. So I have y cubed and y cubed, but that would only get me y to the 6th power. We have one more left, so that y goes over here. Now, when we take the cube root of -8, we know that that's 2. The cube root of x cubed is x. The cube root of x cubed is x, and the same for the y's. But we don't want to leave this as 2x, y, y. Remember, x times x is x squared, so it's 2x squared, y squared, multiplied by what we have left that's not a perfect cube, the cube root of 7y. And this would be our final answer here. Okay, we're going to look at an addition and subtraction problem where we're simplifying, we are adding and subtracting our radicals. And with this one, you just want to be really neat and careful with your work. So I'm going to work with this one in blue first. Okay, so it says 2 times the cube root of 270. So you want to think of 270 and you want to think of a number that goes into 270 evenly that is a perfect cube. So 27 is a perfect cube and it goes in evenly, 27 times 10. So I'm going to split this. So we have 2 times right on the outside. So it's 2 times the cube root of 27 and then times the cube root of 10 because 27 times 10 is 270. Okay, if I work with that here, we know the cube root of 27 is 3. So I have 2 times 3 and then I'm left with the cube root of 10. So 2 times 3 is 6 times the cube root of 10. So that's the first part. Now I'm going to do the next part in red. So we have negative 3 times the cube root of negative 432. So I have negative 3, and now I want to think of a number that goes into 432 evenly that is a perfect cube. So if you look at the list of the perfect cubes on the page before, 216 goes into 432 evenly, 216 times 2. So I'm going to have negative 216, so I'm putting my perfect cube first, and then multiplied by the cube root of 2. 2 is not a perfect cube. So if I simplify this here, I have negative 3 times, now the cube root of 216 is 2, but it's negative 216, so that's negative 2, and then I have the cube root of 2. And negative 3 times negative 2 is positive 6 times the cube root of 2. And then the last part I'm going to do here in green, so we have plus 4, and we have the cube root of 54. So we need to think of a number that goes into 54 evenly that's a perfect cube, and we're going to write that first. Again, put the perfect cube first and then the non-perfect cube. So 27 is a perfect cube that goes into 54 evenly because 27 times 2. So we have the cube root of 27 times the cube root of 2. The cube root of 27 is just 3, so we have 4 times 3 and then the cube root of 2. So 4 times 3 is 12. And then we have the cube root of 2. So remember, when you are adding or subtracting radicals, you have to have like radicals. So you have to have the same index and you have to have the same number underneath the radical or the radicand. So what you can see here is that the cube root of 2 and the cube root of 2, so we can actually combine, and our final answer would be 6 times the cube root of 10 plus 6 plus 12. We can add the numbers outside the radicals and we end up with 30. And then the cube root of 2. We cannot add any further because these are not like radicals. So this would be as far as we can simplify. Okay. Last problem we're going to go through together before you guys practice is number 5. So remember that we can't have radicals in the denominator, which we talked about earlier today. We learned how to rationalize the denominator. And when we think back to what we've learned previously, if we had a binomial in the denominator, we multiplied by the conjugate. So if we had 7 plus 3 radical 5, we're going to multiply the numerator and the denominator by the conjugate, 7 minus 3 radical 5. So let's just review this from before. Okay, now remember you have a binomial times a binomial, so you can use FOIL or the double distributive property. So we're going to do, on the numerator, we're going to multiply 7 times 7, which gives us 49. And then we have 7 times negative 3 radical 5, so that will give you negative 21 radical 5. And then negative 3 radical 5 times 7, again, negative 21 radical 5. And then we're multiplying negative 3 radical 5 times negative 3 radical 5. So remember, negative 3 times negative 3 will give you 9. And radical 5 times radical 5, or radical 5 squared, is just 5. So that would be 9 times 5, or 45. So that would be your numerator. Okay? And for your denominator, we're going to do the same thing, and we multiply or we FOIL. We end up getting 49 minus 21 radical 5 plus 21 radical 5 minus 45. So let's simplify. In the numerator, we have 49 minus 42 radical 5, because they're like terms. We can add these together, and then plus 45 over 49. These cancel. Minus 45, and we can simplify further. 49 plus 45 gives us 94 minus 42 rad 5 over 49 minus 45, which is just 4. And now the 94, the 42, and the 4 are all divisible by 2. So we get 47 minus 21 radical 5 all over 2. Okay, so go ahead and continue working on the practice. You're going to complete 6 through 15, and then you can check the key.